Now, since we've learned everything about linear systems, let's do a little bit of nonlinear systems. Okay, so here is a nonlinear system that comes from the second order differential equation describing a pendulum. So without damping. So recall that basically what we do, we write that x1 equals theta as a function of t, maybe of t, and x2 is going to be theta prime. Well, here is the direction field, and you may notice that in the direction field there are some critical points. So let us try to analyze the critical points. So first, let's find the critical points. So the critical points are those where the right-hand side of the system of differential equations is 0. So we see that x2 is 0, and sine of xy is 0. And if sine of x1 is 0, it means that x1 itself is a multiple of pi. And since sine is a periodic function with period 2 pi, it means that there are two essentially different cases, right? So if, say, 0, 0 and pi 0 are different, but 2 pi 0 is the same as 0, 0, or 27 pi 0 is the same as pi 0. Okay, so now you can try to stop the lecture and try to guess the type of the critical points. And now I will tell you at least what it seems to be from the picture is that here we have some kind of circular motion. So this is a center, and here we have some trajectories approaching, but then going away. So which means that this is a saddle point. So that's a center, and this one is a saddle point. So what I want to say is that here we kind of have something very similar to linear systems. In the next lecture, I'm going to explore this a little bit further, how we can extract information for a nonlinear system from information about a linear system. But now let me tell you a little trick how we can determine trajectories of this system. And the idea is that if we have two equations here, then we just divide one of them by the other one. And the reason it works is because, so recall that it is calculus, so dx1 dt is not the division. So this is not the division. It is differentiation. But the reason the notation is similar to the division is because in some ways it behaves similarly. For instance, if you try to calculate the derivative of dx2 with respect to dx1, then by the chain rule, it is the same thing as dx2 dtt times dt dx1, which is in turn is dx2 dt, and the derivative dt dx1 is the reciprocal of the derivative dx1 dt. That's how we can do it. But then this equation on x1 x2 is a separable equation, which means we can solve it. And here is a solution. So we managed to find trajectories in terms of an equation on x2 and x1. So notice that we haven't solved the system, because solving the system would mean that we must find x1 of t as a function of t and x2 of t. How to do this? I don't know. It may be even impossible. So we don't know this. So we only found an equation on x1 and x2. But still it means that we can plot trajectories in, say, Desmos calculator. For different values of c, you can just go there and do the plotting. And then you will see that these trajectories, indeed, they look like this. So we can just plot them on top of the vector field. And as we see that, indeed, there exist cyclic motions around 0, 0, and there is a saddle-like behavior around pi 0. And then we have seen how we can, the questions now, can we calculate the type of a critical point? So it is indeed a center and a saddle point. And another kind of question is, will there be different types of phase portraits for nonlinear systems that just simply cannot happen for linear systems? So that's two kind of philosophical questions that we are going to explore in the next lecture most. So now let me just very, very quickly go through another similar example. Damped pendulum. So now we can do the same thing over again. And of course, there's going to be the same two critical points. And then you can try to figure out, think of what seems to be the type of the critical point. I will answer it in a minute. You can maybe pause my lecture and try to think about it yourselves. But basically here, if you try to just follow these arrows, then it goes like this. So which means it is a spiral sink. But this one is same saddle point. Saddle point. And this one is a spiral sink. So in other words, here we have not seen new type of behavior as compared to linear systems. But that was just on the intuitive level. So can we do a similar calculation as we did for the first example? Can we determine trajectories of this system? And then we get this differential equation. So recall that in the previous example, what we got was a separable equation. Now it is not separable. And I dare you to try to solve it and say Wolfram alpha. It cannot solve it. So this is not an equation of a familiar or even an unfamiliar type that I know of. So believe me that you simply cannot solve it. So which may be a bit discouraging, but it just means that here the trick doesn't work. Luckily, there are other things that we can do, but I'm going to talk about